Hi, everyone. I'm David Kohn. I work at Timescale. I'm a software engineer there. I'm going to be talking about how Postgres aggregation works and how to create and use custom aggregates. I'm also going to be talking a bit about what we call two-step aggregation, which is sort of a design pattern that we've chosen for some of our custom aggregates. So basic outline. Sorry, I should have mentioned this. I think I mentioned this before, but the slides are available at that short link. And they're just on Google Slides. You can take a look at them yourself. So we're going to go over how Postgres aggregation works through pictures. Then we'll look a little bit at the create aggregate statement and some examples of custom aggregates. Talk a little bit about PGX, not a whole lot, but just give a little bit of a taste of what it does. And then we'll look at the two-step aggregate design pattern. I'm going to breeze through some of the create aggregate statement. If you want me to stop at any time in the talk, please feel free to raise a hand and ask a question. Yeah, so with that, let's talk about how Postgres aggregation works through pictures. And you might know that this is a bit of an ode to Bruce Momgen, who many of you may know. So this is me with a bow tie in honor of Bruce. He does a lot of talks on Postgres internals through pictures, and I always liked them when I was a baby Postgres developer, so a little bit of an ode there to him. So let's talk about what an aggregate is versus what a function is. So an aggregate basically takes inputs from multiple rows, whereas a function is taking inputs from a single row and producing a result. So an aggregate produces one result for a group of rows, whereas a function produces a result for one per each row, taking each of its inputs from that row. So as an example, let's take a look at the difference between an aggregate and a function. We have a table, just a silly table with foo and bar and baz because we like to use those. So the greatest value between bar and baz we can get for each row, that's a function. An aggregate would get the max value over all the rows. Easy. So we're going to do something like this. So how max sort of works is like, okay, if I do select max of bar from foo, then it's going to look at the rows, and it's going to give me the result 3.0. But how does it actually do that? Well, actually, aggregates still work row by row. It's not like it gets to see all of the rows. Could be millions, right? So it can't actually say, like, I'm just going to take all of these rows and like do something to all of them at once. I need to still work row by row. So how does that work? So what we have is we have some state. And as we scan over the rows, one by one, they pass through, and we update our state. So with max, we're just going to say, hey, is this state greater than the last one, or than the one that I have? If it is, I'm going to replace my state. That's the algorithm for max. And as I go through my rows, you'll see that my state updates. So this part, and then I'll output a result. That's the basic gist of how that aggregate works. So that is called the state transition function. So that thing that's doing to say, hey, what's my state now? Let me compare it to the next row coming in. That's called my state transition function. So I can sort of label that part of my arrow that is representing an aggregate over here and say, okay, that's the state transition function. Okay. But what about aggregates with a little bit more complex state? What do we do then? Well, so let's take, as a simple example of a more complex state, let's think about average. So for average, I need to keep the sum and I need to keep the count. Okay, so I do that, and that's nice. And as I go through each of my things, you see that my state still updates. My sum updates as the sum. My count updates as the number of rows that I've seen. And I can just keep doing that as I move through each of my rows. That's nice. But now how do I output a result? Right? I can't just output 6 and 3. That's not what the user asked for. They asked for the average. So what do I have to do? Well, I have to do something. I have to divide. And that's going to be called the final function. So if we sort of put that in pseudocode, the next state is calculated by applying the transition function to the previous state, or I guess the current state and the current value. And then the final function is applied to the final state and produces a result. Easy enough. Okay. So one thing to note here is that the transition function is the expensive part. Why? Well, because we have to do it on each row. Whereas the final function only gets called on each group of rows. So I could call the transition state in this case 3 times, and the final function once. But you could have the transition function called 10,000 times, or 1,000,000 times, and the final function called once, depending on how many rows are going into your aggregate. So we want to optimize calls to the transition function. So one thing that we could do, or not necessarily optimize it, but make that cheaper for the user, one way to do that would be to parallelize it. Okay, so now what I have is I'm going to do 5 rows because 3 rows with parallelization is even a bridge too far for me. So we've got 5 rows here, and we've got 2 instances of our kind of arrow representing an aggregate. The rows, as they move through, we're going to update the transition function, right? For each of these, the transition state, using the transition function. So we have 2 instances of the transition function running now. That's going to reduce the time that it takes for the user to see the calculation. And then, again, we run into a problem, right? We want to output a result, but what we have are actually now 2 transition states. And combining the 2 transition states for average is not the same as taking the next value in, right? For the next value in, I say, okay, I have my sum and my count, and what I'm going to do when I see the next value is I'm going to add that value. Oh, let's even go back, right? I've got 4.02. When I see the next value, I say I need to up my count by 1, and I need to add the value to the other side, and that's what you'll see. So then I get 9.03. But when I have 2 of these, I can't do the count side of that. I need to actually add the counts together and add the sums together. And so that's a different thing than just applying the transition function again. I actually need a different type of function. And that is called our combine function. So a combine function takes 2 partial states, or multiple partial states. Technically, it can be run over, if I had 10 workers, I could combine all of the partial states, but essentially you just apply this repeatedly, right? Each one we get another partial state, so we can just keep doing that. And so that's what we're going to do here. We can see that then our combine function gets to work. So once we have processed all of our rows in each of our instances in parallel, then we apply our combine function, and then we can apply the final function and get our result. So those are the basic sort of 3 steps of aggregation. There are a few other fun things that Postgres does, especially to deal with that transition function being the costly part. So we do deduplication. If I see average bar, and average bar divided by 2, I'm not going to run the transition function, or even the final function, but because we know that transition function is expensive, I'm only going to calculate average bar once, and then I'm going to just put the result in for average bar over there. Great. Oh, sorry. Slides instead that. So now that we've understood that, we can figure out what that means in the create aggregate statement. So all of these things have parts of the create aggregate statement that they're going to apply to. So the sfunc is the state transition function. The final func extra, final func modify, that's the final func. So the final func extra does some things with, if you have any types, then you need to tell it, hey, what kind of output do I produce? That's what final func extra is for. Final func modify, it's normally read-only, and if you start getting into shareable and read-write, read the docs. The combine function, you can see we have that there. And then we have serial and deserial functions, initial conditions, and parallel markings. So serial and deserialized functions basically are the things that say, hey, I have these parallel workers, these parallel instances. I need to figure out how to pass the information between them. So we have some functions that allow you to do that, especially if I have an internal type for my aggregate. Otherwise, you can use an initial condition, which then will mean that it uses the default serialization for that type. I think you can, if you provide a state data type, that's when it's going to use the default serial and deserialized functions for that type. And then you can mark something parallel safe if you want it to be able to parallelize. And then these we won't talk about right now because they're all for window functions, but basically they're moving versions of all of the other things that we just talked about. So they allow window functions to work, and window functions are beyond the scope of this talk because it's long enough already. So let's talk about some examples of custom aggregates. We'll start with SQL, then we'll move a little bit to the Rust and PGX side. Happy to answer some questions around that stuff. So let's think about sort of making our own custom aggregate to do some things that the normal Postgres aggregates already do and probably do better, so don't actually do this, but this is just to give you an idea of what you would do if you wanted to create an aggregate yourself. So we'll make a statistical aggregate. And our initial condition, so we might make a type for it to use. We'll have a counter, which is n. We'll have sx, the sum of x. That'll be a float. And sxx, which will be the sum of x squared. That'll also be a float. This is not a good way to actually do this. It's actually very numerically unstable, and when you do this for real, you should use a different algorithm. We do that in our stuff, and Postgres does that inside. So don't actually use this algorithm, but it's the naive way of doing it, so we'll just talk about it. So our transition function basically says, okay, whenever I want to return this type, and whenever I see a new value, like I'm going to take in a version of this type and a value, when I see a new value, I'm going to add 1 to my count. I'm going to add the value to my sum. And I'm going to add the value squared to my sum of squares, right? And this means that I can do things like calculate the average, calculate the sum, calculate the count, calculate the standard deviation. All of those things are going to come right out of this sort of data structure. And then I can create an aggregate. You see that I denote my s function, s type, my state transition function, and my internal state type. Sometimes that s type, by the way, in your custom aggregates, especially if you're using something like Rust or PGX, will be called internal. That means you're handling that. So it doesn't deal with all the type checking and anything like that. And then you can provide an initial condition. And we'll provide an initial condition here of 0, 0, 0. Okay, so if you want to test it, see what it outputs, cool. We can test it on just like a generate series here. Seems to work nicely. Then we might want to provide some final functions. So I would take this stats thing. I would say, okay, well, if I want to get an average, I need to divide my sum by my count. If I want to get a variance, well, then I'm going to that's the formula for variance. I'm not going to read it aloud to you. You can look at it. And standard deviation, similarly, right? So pretty easy. I can then apply those, and I can now make simple aggregates using those final functions that I've just defined in SQL. Cool. So that works nicely. You see that it kind of works. How about the combine function? Right, so that would be the last thing that we need, and then we can mark it parallel safe if we do that. So we can write a combine function, reapply, and you would do that for all the other aggregates that I just made, right? Same sort of thing, just specify the combine function. So pretty simple in general. So what we've done though, and what many people do when they want to do things like this, is that they'll use some other language. You can use C to develop aggregates, it's often a bit faster. You can use PGX, which is what we use, which is a Rust-based framework for developing extensions for Postgres. And there's a lot of nice things that it provides. I'm not going to read them all to you, but it really helps us manage all of the complexity around managing a lot of objects, a lot of different types, a lot of aggregates that have a little bit more complexity. Some of the things that I like about it are the mostly automatic schema generation, type conversion, and at least a fair amount of Rust's inherent safety, so you don't have to worry as much about seg faults and the like, as when you're developing in C, say. So for us, it manages over 600, and this is the toolkit team, the timescale toolkit, which has a number of hyperfunctions, which is some of the stuff that we call some of these aggregates that we work with. So we have over 600 custom types and functions that are managed by this, and frankly, if we had to do all of the SQL ourselves, it would really be horrible. It's really nice that it just generates it for you. So some of the other things that I recommend and that we've done is we split each of our sort of types of functions into their own crates. Then we can test the code separately. So for our stats stuff that we were talking about, I have an accum function, right? This is going to essentially be the transition function. Now, we're using here the Young's-Kramer method, which is basically a way to do this in a numerically stable way when you're working with floating point arithmetic. Otherwise, you get potentially very large error. So we can put that in itself, test it separately, so we don't have to always spin up a whole Postgres instance in order to run our tests. So we can do a lot of the logic in Rust, use its own testing framework to do that. And then when we put it together, we still have sort of integration tests in essence with Postgres, but a lot of the logic can be tested separately from that, and it makes the tests run much faster, et cetera. And then there are macros. They're getting sort of replaced right now as PGX goes into its next version, where we're also going to be working on making some better things to manage aggregates themselves. Because right now you still need to basically write your own create aggregate statement. But at some point soon, hopefully, we're going to contribute back some things to PGX to make doing the aggregate stuff a little bit easier, and it will generate all this for you. So that's some stuff that hopefully will be coming back down the pike. But it does manage some of your dependencies, as you can see here. So you do have to specify them, but it'll make sure that it orders things correctly. So it says, hey, I need all the transition functions and combined functions before I can run this SQL statement. So I know now which order I need to run things in order for it to work. It's pretty cool. So now we'll talk about some things that we do in the toolkit that actually build on what Postgres does on these types of things. And it's the two-step aggregate design pattern and why we chose it. I talk about it partially because I think that it's actually a really nice design pattern for a lot of users and things that you guys can use also as you're building your own aggregates. It basically exposes, so it works basically like this. Instead of just having something like select average of value as the average, we're going to do essentially just take the stuff that we just went over in Postgres and expose it to the user a little bit. And I'll tell you why in a minute. So we'll have statsag, and then you calculate an average on that, or approximate percentile. And we have percentile ag inside. So we have an inner aggregate and an outer accessor. And essentially, what we're trying to talk about is like, why don't I just have the one-step sort of aggregation system? And basically, we're taking everything that's in the Postgres aggregates and doing something very similar, but exposing it to the user. So the transition function is basically like the aggregate. The final function is basically the accessor. And we also have something called rollup that allows you to then roll up these aggregates into larger buckets or larger ranges or whatever else you want yourself, so that if you've stored an aggregate and materialized it, you can then roll it up at a later time. And so Postgres will let you do this with things like in the aggregate statement itself. You can do things like rollup or group by cube, right? But you can't say, okay, I'm going to do create materialized view, select average of X, and then come back a week later and say, hey, I want to take the stuff that's in that materialized view and roll it up another level. Because then you're not actually going to get the average, you're going to get the average of averages, which is not the same thing. So rollup lets you do that. And it's a common thing for all of our aggregates. So all the aggregates that we're creating that allow it have a rollup function where you can just go in and say, okay, I want to roll this up, I want to take it to the next aggregation step. So in general, the way that we always want to do this is like play within the SQL language, make it useful for a few rows of data, but high performance for lots, and try to make it as intuitive as possible. And basically try to make things, I guess, fundamental things simple and advanced analysis possible. So let's think about some reasons for the two-step aggregation. We allow multi-parameter aggregates to reuse state. So when we talked before about how we could do deduplication, and we could reuse the result. We can calculate the average once, reuse the result. Well, what if I did it a different way? What if I did it like that? I did average of val and average of val divided by 2 instead of average of val divided by 2. The planner can't figure that out. right? It doesn't know that this is a simple linear transformation of the overall result, and that I can just do this transformation. It would be very difficult to program that into the planner, even though we can see it very easily. So we have to speak in a way that the planner can understand. And we want to make it hard for users to write low performance code. So if I have something like approximate percentile, where I have two inputs, right? I have the percentile I'm trying to approximate, and I have the percentile ag. If I just did something like this, right, where I passed in the value and the percentile, well, I can't deduplicate that because these are moving. So instead, we want to be able to the planner to be able to very easily treat it the same as, hey, I could do it in a subselect and then run my approximate percentile on top of it. So all of that stuff is then handled for the user rather than you having to do it yourself. And that's another thing that we like. And so now we hear, you can see, now we have the deduplication because our aggregate argument is constant. Are people following? Am I losing people? Is this good? Good? Hey, thumbs. I can see them, unlike when I'm doing this in a virtual context and I have no feedback whatsoever. This is nice. Yeah, so, and this is just to, like, again, reiterate, transition function called once per row, the final function is called once per group of rows, and this is the same thing for our aggregate, right? So it's also going to be called once per row, whereas the accessor is going to be called once per group of rows. So it also means we can just use multiple accessors. So now we have the same aggregate that's getting called throughout, but we have different accessors that take different numbers of arguments or different types of arguments. And that just like works out of the box and makes a little bit more sense, at least in my mind, rather than having multiple aggregates that like take in different arguments and are slightly differently named, that are actually doing the same thing under the hood, but the user can't quite tell. It's just a little easier and simpler to understand if we just say, hey, here's the aggregate, here's the accessor. This design pattern is actually pretty easy to understand once you have it explained. So like, let's let you use it and build on it. So yeah, so this is the next thing is to cleanly distinguish between parameters that affect the aggregates versus the accessor. So let's look at an example of that. So right now, we did approx percentile. We were using, there's essentially an underlying algorithm to approximate a percentile, right? And the reason, by the way, that we made approx percentile or something like that is that the the exact algorithms that Postgres uses just can't be fit into a framework like this. You can't actually materialize them ahead of time and combine them. You can't, they're ordered set aggregates, so you can't, you just need all of the data. You also can't parallelize them. There's various things that, like, they're good, but sometimes approximations are better for very large volume data use cases. So we have our sort of default option, which is percentile ag, as we were talking about before, and then we have the underlying algorithm for that, which is UDD sketch. And that has some parameters. So percentile ag has some default values for those parameters, but you can specify them yourself. So now imagine that I had all of those parameters for my aggregate, along with the value, and the percentile that I'm trying to calculate. Well, which ones are going to affect the aggregate? Which one are going to affect the final function? Like, what's going on? It's just very difficult to read, I find anyway. Whereas here, it's very clear. Like, these are the things that are affecting the aggregate, whereas those are the things that are affecting the accessor. So, yeah, and this just is a little bit nicer version of that. Okay, so we were talking about rollups before. Let's go deeper into rollups. So what we talked about before, right? The sum of the sum does, in fact, give you the new sum. Same with the max or min, right? Those are fine. But things like average, standard deviation, all of those things don't really work. So if I were to do something like with our continuous aggregates, where I produce a continuous aggregate with some average and percentile ag, I know that I can roll up percentile ag. I don't know that I can just keep going with some or or aggregate. So rollup is this keyword that now allows us to say, hey, you can reaggregate this. It is safe to do. And if there isn't a rollup, then it's not safe to do. That's it. So this is very simple to reaggregate. We can just like do that at query time. It's very easy to do. And then we also have things like rolling. So this allows us to use it in window functions. For the most part, it's just a slight change to the keyword, but we also actually provide those inverse transition functions for some things, whereas we don't in the rollup case. Just depends on which one is which, but rolling allows you to then do that in a window function context. So this allows you to create tumbling window aggregates, which are actually really, really helpful in a lot of cases, especially with continuous aggregates, but also actually just in general in some cases, because you don't actually want, like if I have 1 million data points and I want to create a rolling 15-minute average, like I don't want the rolling 15-minute average for each of my 1 million data points. What I actually want is every minute to have a rolling 15-minute average. And doing that in SQL without something like this gets really difficult, like surprisingly difficult. I have to go and do it myself, and if I want the rolling 15-minute standard deviation, then like, good luck. Like, because with the other stuff, well, I guess I can do the sum and the count, like, and then divide myself. Like, that is possible. But like, do I really want to be writing the full standard deviation calculation in SQL to try and figure that out? Like, this is not user-friendly. It's not something that we want to do. So in general, I try to design my aggregates this way. I'm already doing it so that I can work within the Postgres framework to work with, so I may as well expose that to the user, is my basic thought. And so then the sort of final thing is that this allows easier retrospective analysis of downsampled data. So with our continuous aggregates, we allow downsampling of data. So basically, you just keep the aggregates and throw out the underlying data. It's as if you had a materialized view that like could still be updated at the front as new data comes in, but at the back, you can get rid of the underlying data and just keep the aggregation. So the problem is, like, I can't go back and reanalyze that data if I want to produce a different aggregate, right? So I can't say, hey, okay, so right now I want something like I have a 15-minute aggregate, and I just put the and I want the 90th, the 50th and 90th percentile. If I come back tomorrow and I want the 99th percentile, well, what do I do? Well, with this, I can just calculate the 99th percentile because I just use my accessor. That's easy. So all I do is I put my first step, the aggregate, in the calculation, but I don't actually essentially finalize it because there's more information there than the user's using. So if I come today and I want the average, and tomorrow I also want the standard deviation, or we allow for some third and fourth order moments. So if I want the kurtosis, then I can come back and get that. And I can get it on the old data, which otherwise I just wouldn't be able to do. So that's basically, sorry. Again, I have slides for things that I just talk about. So if my requirements change and I need different things, the other thing that it allows us to do is rebucket. So if I want to go from a 15-minute aggregate to a one-day aggregate, I can just do that. Again, simply, easily. It's nice. And so the basic impact of that is we want to change the query, not the underlying aggregate. Rewriting that table, even if we hadn't thrown out the data, rewriting that table is a long process. It requires a lot of extra work. Why would I want to do that? Much better to just change my query that's going at runtime. So that's about it. That's the link to the slides again if you want them. I have no idea what my time is or how much time I have for questions, but I'm happy to take any questions on this or any other topic that you have. Somehow, probably I got through, yeah, of course, I got through 118 slides in half an hour. So, yeah, so questions? Yeah, so the question here was okay, so let me try and summarize it and see if I get it right because they need it for the recording, I think. Aggregates look kind of like a finite state machine, and he was wondering I don't know your name, sorry. I was wondering whether the aggregates, if you could control the order in which you process events so you can do things like event sourcing with them. So there are a few things there. So first off, you can put, if I could type, I could show you, but you could put an ordering into your aggregate statement. So you can actually say in an aggregate, you can say order by foo, right? So that's one way that you could handle that. And you could make an aggregate that requires that. We've thought about doing that. The way that we handle it, though, is that we tend to just build up a buffer of events. So there are certain, these ones are not, but we have a few aggregates that are technically not parallelizable in the Postgres sense, because in Postgres' sense, if you parallelize, you're just sending things to whatever worker you want. But we can use them in continuous aggregates because we need that ordering. So things like time-weighted averages and counter aggregates that rely on the data being in order when we get it, what we basically do is we build up a buffer in the transition function, basically an array of whatever data type we have. We then take that data type and we sort it by time, usually, for us. And then we process that in either before we run the serialize function or before the final function is called. And then we produce some state. Usually when we're looking at those aggregates, one of the things that we need to do in order to enable rollup is that we actually need to then keep the first and last values so that we can then combine the states between the adjacent pairs. And then we will have some internal state. So essentially what our transition function looks like is build up an array and then eventually apply this thing. The combine function can still do what it needs to do because we have stored the adjacent values that would be between any two. We then, in our combine function, actually need to build up another array of those states, sort them, and if we have overlapping state, we error. So that's how we handle it. I'm not going to say that it's the best way to handle it, but it's certainly the way that we've found useful. We're going to be doing some things also to allow that to spill the disk if it really needs to, because certainly there's some memory pressure problems there. But that's what we've done in order to handle that sort of stuff. If that's useful for you. Okay. I think that's it. Thank you, guys. Lovely.